we're asked to consider a spinning string of length 2 and linear density 0.1 and tension 3. We want to find the smallest angular velocity when the string pops out. We can model the situation using the differential equation T y double prime plus rho omega squared y equals 0, where rho is a uniform density, omega is the angular velocity, and T is the string tension. Looking at the graph below, where the string is attached, we have y of 0 equals 0 and y of L equals 0. In our case, notice T is equal to 3, rho is equal to 0.1, and L is equal to 2. This gives us the boundary value problem, 3 y double prime plus 0.1 omega squared y equals 0, where y of 0 equals 0 and y of 2 equals 0. For the next step, we divide the differential equation through by 3, which gives us y double prime plus 1/30 omega squared y equals 0. We are now looking for the eigenvalues of y double prime plus lambda y equals 0, where lambda is 1/30 omega squared. We normally consider lambda less than 0, lambda equals 0, and lambda greater than 0. However, we only need to consider lambda greater than 0 here because lambda is equal to 1/30 omega squared, and we know omega is positive. When omega is greater than 0, the corresponding characteristic equation is r squared plus lambda equals 0, where the roots are plus or minus I square root lambda. So because we have two complex roots, the general solution is y equals a cosine square root lambda x plus b sine square root lambda x. And now we consider the conditions y of 0 equals 0 and y of 2 equals 0. Let's begin with y of 0 equals 0. If y of 0 equals 0, then we have the equation a cosine 0 plus b sine 0 equals 0. And since sine 0 is 0 and cosine 0 is 1, the equation is only true when a equals 0. So if a is 0, we now know that y is equal to b sine square root lambda x. And now we consider y of 2 equals 0. For y of 2 equals 0, we have the equation b sine of square root lambda 2, or 2 square root lambda equals 0. This equation is true when b is 0, which we don't want because we're looking for non-zero solutions. It's also 0 when the input into the sine function is a multiple of pi, which means in our case, the equation is also true when 2 square root lambda is equal to k pi, where k is an integer greater than or equal to 1. Solving 2 square root lambda equals k pi for lambda, we divide both sides by 2 and square both sides, which gives us lambda equals k squared pi squared divided by 4. But recall lambda is also equal to 1/30 omega squared. This indicates the positive eigenvalues are lambda equals k squared pi squared divided by 4, which equals 1/30 omega squared. And because we're looking for the smallest angular velocity when the string pops out, we need to solve for omega. We do this by first multiplying both sides by 30, and then taking the square root of both sides, which gives us omega equals the square root of 15 halves times pi k. From here, because we're looking for the smallest angular velocity when the string pops out, we select the smallest value of k, where k is an integer greater than or equal to 1. So we let k equal 1, and therefore the smallest angular velocity when the string pops out is square root 15 halves times pi radians per second. I hope you found this helpful.